You can see it. Good. Hello and welcome back to Calculus 1, section 4.9 on antiderivatives, integrals. So this is the last lesson of 4.9, which opens the chapter on integration. The next three chapters are on integrals. Now, some of those are in Calc 2. We are going to see sections 4.9 through 5.5 in Calc 1. That's going to be basics of integration. And then the methods and, bit spicier stuff regarding integration is all in Calc 2 for those of you going to Calc 2. So to start off here, we are hopefully familiar that the derivative of x squared is 2x. I'm going to now write this backwards because antiderivatives are going to do the backwards procedure here. So integral of 2x dx is going to be x squared. Now, this is not the end of the story. Leave some space here, I need it. Now, the second example is x squared plus 10. What's the derivative of x squared plus 10? 2x. So the integral of 2x dx is x squared. Do we see the issue? Derivatives annihilate this piece of information, which is plus 10, the constant. Now, even if I have a subtraction there, so if I have, let's say, x squared minus 2/3, it's still going to be 2x, and the integral of 2x again is going to give me back x squared. So we have issues with constants. And for that reason, you are required, under penalty of death in calculus, to put plus c every time you integrate. This plus c is not there for decoration, right? It's there as a placeholder for the unknown constant that was annihilated by differentiation. You don't know what that number is, and if you have additional information, you can figure out and calculate what that number is, right? So right now, we know this. Now, what do these numbers do when you have them in your x squared, right? So you know that your x squared is going to be a parabola going through 0. That's your x squared. But then you have another parabola that's going to go through 10, and that's your x squared plus 10. And then you have a parabola here that is going to go through negative 2/3, right? So all this extra number did, this constant number, right? All that this number did is this number shifted this function up or down. That's all it did. Now, when you do integration to retrieve this x squared function, what you are getting, from a single integration, you are getting infinitely many of these. They're everywhere. They're at every point. They are so closely packed that I could just graph like this, like literally just, color everything in black, because they're so densely packed. Any space that you have in between, you can fit infinitely many of these parabolas in between. Because those parabolas have to go through every single number, every single value on the y-axis. Well, that's infinitely many of them. And when they stack so densely, so close, right, it's just going to be a completely filled in black blob, right? And these parabolas open up forever, so just the entire space is going to be, you won't be able to see anything. Now, is there a way to compute this C? And the answer is yes. if you give me any point, what we call initial condition, if you give me any point in the xy plane, I will be able to retrieve C. So here in red, given initial condition which is just a point, we can calculate C. So now, find C given 319, whatever, just whatever point. So what do? Well, we plug in, exactly. What is our function? We had that the integral of 2x dx gave us x squared plus c. So I have that my function f of x, we use capital F in here, f of x is equal to x squared plus c. Guys, please put capital F of x, because the lower f of x will be reserved for the function that goes into integral. Okay? So the result is capital F of x, which we call antiderivative, and lower f of x goes inside the integral, we call that integrand. So capital F of x is x squared plus c. All right, so now I have a point, 319. So 19 is equal to 3 squared plus c. So 19 is equal to 9 plus c. C is equal to 10. And we retrieved one of our original problems. You see that x squared plus 10? We retrieved that one. So that function goes through 319. And we have x squared plus 10 as our antiderivative. So, anytime you integrate, you must put plus c. If you have this extra piece of information, you are able to calculate the value of c. In vast majority of cases, 99% of the time, you will just leave it as plus c because this information is not provided to you. This translates later on through differential equations into, let's say you are baking a turkey, right? You can stick the temperature probe into the turkey, read the temperature of, let's say, 107 degrees after, I don't know, an hour and a half. And now you have hour and a half, that's going to be 90 as a input value, x equals 90, and then capital T temperature, right? It could be, what did I say, 107. So 90, 107 is a point that you will be using to calculate C. You will be calculating this C almost all the time in differential equations. But now in Calculus 1, 2, and 3, rarely, very rarely. So you need to know this procedure for how to find. It's very easy, right? You just, whatever you get, call that a function and just plug the value in. So, what is the rest of this lecture about? Well, all antiderivatives that are basic antiderivatives which you guys have to know. For instance, integrals are backwards, right? So if you know the derivatives, then you should think derivatives backwards and you will have your list of integrals. There is only one formula that you will learn tonight. One. The rest of these formulas, in this lecture, the rest of these formulas you already know as a derivative formula. Let me give you an example. The derivative of the constant is 0. What is the integral of 0? Well, it has to be a constant. Now, Integral of 0 is 0, but then you have plus c, and that's where you get it. So integral of 0 dx is 0 plus c, and that's how you get your c back. Okay? Now, the derivative of the x to the n was nx to the n minus 1. This is the only formula that you are technically learning. The derivative of x to the n dx is x to the n plus 1 over n plus 1 plus c. So that's the formula. And then the rest of the formulas you already know. We have the 6 trigonometric one, exponential, logarithmic, all of these formulas you already know. Before we actually go into any of those, let me just remind you real quick that your nth root of x is also x to the nth power, so it belongs there, right? And your fractional, right, x to the n is x to the negative n, also belongs there. So polynomial, rational, and radical, all of those belong in the single formula, just like they belong there with the derivative, right? One formula for all of them. So this is one of the big ones. Now, the derivative of e to the x is e to the x, which means integral of e to the x dx is e to the x plus c. Nothing new, nothing exciting. The derivative of ln x is 1 over x. Integral of 1 over x dx is ln absolute value x plus c. I'm going to write here in blood. Absolute value is a must. Otherwise, you will lose 1 or 2 points depending on the current mood. And I need to explain why absolute value is a must. So it's just, it's not an arbitrary rule because I'm a terrible person on Wednesdays. Please note the domain on the left-hand side inside the integral. What is the domain of 1 over x? 1 over x is a function which you graph to the left and to the right of the y-axis. The domain is from negative infinity to 0, union 0 to infinity. What is the domain of ln x without absolute value? The domain is just on the right-hand side, 0 to infinity. Do we see an issue? Because if I am allowed to plug in negative 3 on the left side of the formula, I better be allowed to plug in negative 3 on the right side as well. Does that compute? So, ln absolute x has domain exactly the same as the domain of 1 over x. So absolute value is not optional in this formula. You absolutely must have it, right? You must have the formula with absolute value. I had students before try to make the argument, why am I losing 1 or 2 points? I only forgot the absolute value, right? I demand my points back. You actually killed half of your domain. So you should be losing 5 out of 10, not, right, for that kind of mistake, not 1 or 2. If we are going to look, right, into details. So again, why is this the case? Can I plug a negative 3 here? Sure, I just have negative 1/3. With absolute values, I can plug in negative 3 and we're good to go. Without absolute values, ln of negative 3 is a complex value. It's not real, right? So we must have absolute value that will kill that negative, and once it kills the negative, we're all good. So we have our constant. We have our, well, that's a 0 actually. We haven't done constant yet. I'm going to do constant now. We have a polynomial and rational radical. We have our exponential, and we have our 1 over x, which produces ln. And then let's go with, actually no, now that we are still talking about ln, let me write something in blue over here, which is another clarification. Didn't we have the formula that deals with rational functions with exponents? Because we can write this as x to the minus 1, right? Can't we just use this and solve it? And the answer is no. Because if exponent is negative 1, what happens in denominator? Right? 0. So you see why, out of all possible exponents that you can have here, the only one that is excluded is a negative 1, which has its own formula in its ln. Isn't this beautiful? The mathematics like falls into, like, the only one that you are not allowed to use here as the exponent is negative 1, because that would create 0 in denominator. You would have x to the 0 divided by 0, and that's an explosion, right? So very, very convenient for that negative 1 exponent to show up and give us ln on the other end. So that's that. All right, the next one. The next one is a constant. So if you have the derivative of, let's say, I don't know, 3x, that will just give you a 3 on the other side. So the integral of a constant, let's use the constant k, dx, is going to be kx plus c. K is some kind of constant, like the 3 on the other side. So that's there. And finally, we are just going to list the 6 trigonometric functions, and then the 2 inverse trig functions, and you have a full list of all antiderivatives, all of which you know, reading them backwards as derivatives, except the n plus 1 one. So now, what do I have? The derivative of sine x is cosine x. What's the integral of cosine x? Dx. Sine x plus c. Plus c. Now, what's the derivative of cosine? Negative sine x. So what's the integral of sine x? It's negative cosine x plus c. Opposite, guys. Opposite from what you have from derivatives. Well, these are called antiderivatives, so of course it's going to be opposite. Right? It's common sense. So your derivatives will give you negative on cosine, your integrals will give you negative on sine. So be very careful about that. A lot of mistakes in Calc1 finals and so on, right there. By the way, everything that I'm talking right now is 4.9 included on exam 3. And then again on the final, right? All of this is exam 3. What's the derivative of tangent x? Very good. So now integral of secant squared x dx is tangent x plus c. All right, so this is where we start going crazy a little bit. What are your basic trig functions for derivatives? Sine, cosine, tangent, cotangent, secant, cosecant, right? What's your basic function for integration? It's a secant square, not a secant, right? So all of these guys that are called basics, only sine and cosine are the ones that are truly basics. The other four, they're all going to be these guys. Here it is. The derivative of cotangent x is negative cosecant squared x, which is integral of cosecant squared x dx to give you negative cotangent x plus c. The derivative of secant x is secant x tangent x. The integral of secant x tangent x dx is secant x plus c. Yes. And finally, the derivative of cosecant x is the negative cosecant x cotangent x, which gives us the integral of cosecant x cotangent x dx to be negative cosecant x plus c. These are not fun at all, right? You have the list of 6 integrals, and only 2 of those are basic in a sense that you guys are used to. Integral of sine and integral of cosine. The rest, secant squared, secant tangent, and cosecant cotangent. None of those are just basic. Now, are we ever going to talk about integral of tangent x? Yes. But not until we go to 5.5. Are we ever going to talk about integral of secant x? Yes, but in Calc 2. All right? So those are not actually basic integrals, and we have to use integration techniques to work those out. The integral of secant x is ln absolute value secant x plus tangent x. I know, right? So, yeah, welcome to Calc 2. Did I mention that Calc 2 is going to kill you with trig? Let me underline that. Calc 2 is going to kill you with trig. So you make sure you review exactly the things I tell you to if you're signing up for Calc 2. Especially if you're signing up for Calc 2 in the summer. All right. So these are our basics. If I had to add additional one, it would be the inverse tangent. Inverse sine shows up once or twice in Calc 2 and once or twice in differential equations. But inverse tangent is going to be everywhere, right? I did talk about that multiple times in this class. So the derivative of inverse tangent of x is 1 over 1 plus x squared, which means that if you run into the integral that looks like that, the answer is inverse tangent of x plus c. So everything that I listed in these, formulas here is broken into 3 different tables in your 4.9 section in the textbook. So when you flip through pages. Now, those of you, I see that some of you have textbooks in class. In the back of the textbook, there is a table, a list of, I believe, either 105 or 106 integral formulas. I think. Was it 105 or 106? 106. So in the back of the book, and you have to memorize the book. So you will find these ones that I listed in the first 10, right? So you will find the ones that I listed at the beginning of that chart. So it's on the cover of your textbook. And there is a section in Calculus 2 in chapter 7, I think, or no, chapter 8. In chapter 8, there is a section labeled integration using the table of integrals. So the entire section devoted just to the ways to solve these integrals. So now, when we are talking about integration, hopefully you guys already understand that these antiderivatives are backwards derivatives. I hope I demonstrated here that every single formula for integration that I placed is simply the backwards formula from derivatives, with the exception of the polynomial one, but they're close, right? One is n minus 1, the other one is n plus 1. The one is multiplying, the other one is dividing, so they are still opposites, right? To some extent. At the beginning, this is your beginning of integration. So in the beginning, it is good to have this habit of thinking, so which function would give me this as a derivative? And that will be your answer for integral, right? Unless you are really computing stuff. So let's take a look at some of these basic integral calculations. For instance, what is the integral of x to the 9 dx? You would say x to the 9. That's a polynomial. You scroll up to the polynomial formula, right? And polynomial formula says that you are supposed to increase by 1, divide 9 plus 1, plus c, x to the 10 over 10 plus c. Green? What is the integral of cube root of x dx? Yes, we first rewrite this as x to the 1/3 dx, and then we follow our rule, and the rule is x to the 1/3 plus 1 divided by 1/3 plus 1 plus c. We're not done yet. X to the 4/3 divided by 4/3 plus c, which is 3/4. You don't want the double fraction hanging around, right? So 4/3 from the denominator goes up as 3/4 as a flip. Do we all know that? When you're dividing by a fraction, you change it into multiplication and then you flip it, right? X to the 4/3 plus c. Good. What is the integral of 1 over 4th root of x dx? Anyone?
So 4 over 3x to the root 4.
No, first I need to rewrite. Yes, very good. It's a negative exponent of 1/4. And then you will add 1. Oops. And then plus c, which is x to the 3/4 divided by 3/4 plus c, which is 4/3 x to the 3/4 plus c. Great. Now, notation. Integral of f of x dx is equal to capital F of x plus c. If you don't have red pen with you, use blood. I'm not joking. Why is this so important? Well, we need to discuss a few things. In about 30 minutes, we are going to see something that will hint what this squiggly line actually is. So we'll skip that for now. It's good enough in this lecture to know that that's read as the integral, and you can also understand this as the instruction what to do. You know instructions, license and registration. It's a very clear instruction, right? So if you see instruction like this, you know that you are supposed to take the derivative. If you see instruction like this, you know that you are supposed to integrate. So that symbol has its meaning, right? But it also has its meaning in math, and we'll see what it is, as I said, tonight, later. Function, nothing new there. Now, this dx. So, it's not optional to write this, because it tells you the variable you are integrating in respect to. The other letters become constants and parameters. So it is not optional to put dx there. You must have it. Now, there will be also a mathematical reason by the end of tonight of why you absolutely must have dx there. But, as I said, for the first lecture, you say, this is my instruction, and this is what I am integrating in respect to. I will give you an example. Integral of a x dx. Well, in this particular example, a is a constant because this x is telling me that x is a variable. So the answer would be ax squared over 2 plus c. A, constant, x, variable. And it is this way because dx. Next row, same problem, dA. The rows are now switched. X is a constant, a is a variable, plus c. So x is a constant and a is a variable because of dA. The first time this is going to hit you very hard is Calculus 3. Calculus 3, you have third-dimensional integrals, triple integrals, double integrals, and all these kind of things. And when you write a triple integral, and you have some kind of function in here, dx, dy, dz will tell you which integral belongs to which variable. So the first integral would be a z, the second one is y, and the one is x inside, so they are paired like that. That's Calc 3. So it is extremely important to understand that these dx's and dy's and all of this, they're not optional. they have to be there, and they actually pair with their symbol over here, and they work together. As soon as you integrate, both of those symbols go away. You all understand, like my algebra students, most algebra students have an issue with the square root. I don't know why, but for 10 years, right, I've been seeing the same thing. Square root of 16 is equal to square root of 4. No, it's not. It's just 4. You used up a square root to turn 16 into 4. So you do not put square root again. Once you integrate your x dx into x squared over 2 plus c, you do not put another integral or dx. They are used up to change the function into another function. Okay? So just like your operations before, right? You can use also 2 plus 3 is 5. You don't say 5 plus, right? Plus is used up to combine 2 and 3 into a 5. Now, operations, subtraction, division, multiplication. Operations combine numbers and change numbers into another number. So 2 and 3 are changed into 5. I can also change 2 and 3 into a 1 by saying 3 minus 2 is 1. I can change 2 and 3 into 6. 2 times 3 is 6, right? So I can use different operations to change numbers into different numbers. When you are talking functions, you have operations to combine functions, but you also have operators. And that's what derivatives and integrals are. Operator changes a function into a different function. Do you see how my linear function x is changed into a quadratic function, right? We have more extreme cases. The integral of 1 over x dx is ln absolute x plus c. So now you have a rational function, 1 over x, changed into a logarithmic function. So integrals and derivatives, they change functions into different functions. What's a noble example? Noble exception is, in terms of derivatives and integrals, they change functions. E to the x is a noble exception because derivative of e to the x is e to the x and integral of e to the x is e to the x, right? So that one stays unchanged. Eventually you will learn that that is the eigenvector for function space. Anyway, now, all of this story was here just to prevent my allergies kicking in. And these would be the allergies towards you as operators of calculus, right? Make sure you have integrals and dx's everywhere. Make sure you have your plus c's. Make sure you do not have integrals and dx's on the right-hand side once integration is done. So that was a talk on notation and importance of these things. Now I am going to talk about it again once we find out more stuff about this. The last thing over here before we do a whole bunch of examples would be some properties that would help you compute these further. So properties. Number one, integral of a constant times a function dx, you can kick constant outside. Same rule you guys had for the limits and the same rule you had for derivatives, right? You can kick constant outside. Rule number two, if you have integral of a sum of two functions, you can do separate integrals. So each one gets its own integral and its own dx. These are f of x and g of x over here. There we go. And number three, if you have a subtraction of two of these, then each one gets its own integral, and then when you're done integrating, you will just be subtracting functions. Do you remember how multiplication worked in the derivatives? You had a special thing going. What was the special thing? What was the name for the special thing? Product rule, right? So we are going to have forms of product rule here that will be studied in Calc 2. You had a quotient rule, right? We will have forms for quotient rule, division of two functions, again, in Calc 2. So this is where we stop with properties in Calc 1, and then the product rule and the quotient will be addressed in Calc 2, and they will be known as integration by parts. They will be known as partial fraction decomposition and stuff like that. So multiplication and division rules exist. They are just not in Calc 1. It's right separated. Does that mean that you are not going to see product and stuff? No, because you already know some of the stuff. For instance, if I have integral of x squared times x plus 3 dx, what should you do to integrate this? Remember, you do not have product rule until Calc 2. Yes?
Multiply it, make a polynomial.
Exactly, perfect. So you are going to multiply this out, and then you will deal with what's left. Now, x cubed plus 3x squared dx. So the first step was to distribute. You might have to FOIL, you might have, depending on how annoying the problem is. So then, after that, now guys, you will be skipping these steps. You will be skipping these steps next week already. But for now, just to illustrate the blue formulas we had, I have summation of two functions, so I can separate these into two integrals. And well, this is f, right? That's f.
Okay, so you don't need it. Right. Okay, it is.
Right?
I see that.
That's f. That's f and that's g.
Right.
So now that's f and that's g, right? So we're good. Now, for the second integral, I can also use the rule and kick the 3 out. So let me just swap them. Right? So now, as you can see, we are dealing with basic integration. X to the 4 over 4, right? You add 1, plus copy this 3, and then you have x cubed over 3 for integral of x squared. And then we put only 1 plus c, because there is really no need to go plus c1 and then plus c2 so that you can combine them into a general plus c, right? So only 1 plus c per integration. These 3's will cancel for a total of x to the 4 over 4 plus x cubed plus c. Now, as a student, I loved, absolutely loved integration, even though integration is harder. And the reason is you can check and know 100% of the time that you are right. All I need to do to check is what? Find the derivative of the answer you have. It has to land into the what you differentiated, and then you can factor and go back into original problem if you want to. So if I differentiate this, it better land me here, and it will. The derivative of x to the 4th over 4 is 4x cubed over 4 plus 3x squared, and the derivative of c is 0. 4's are canceled, and 0 goes away, right? So we have the problem. So I will agree with you that integration is going to be tougher, but this is a blessing that we have. 100% of the problems you should be able to check like this in 10 seconds and know immediately if you are, I mean, presumably that you care, right? If you don't care, just don't worry about any of that, right? You just write whatever answer you think and just keep walking, right? But let's say you care. You can just do this derivative in 10 seconds on the side, and you immediately know that this answer is solid. And that goes, guys, that goes through Calc 2 for the first 2 exams, right? First 2 exams are all integration. And then exam 3 is the problem situation. So for Calculus 2, exam 1, chapter 6 and 7, integration, and then chapters 8 and 9 on exam 2, all integration. And some sporadic derivatives and limits, a lot of limits. Good. So now, what is the integral of 5e to the x minus 10 over square root x dx? Note that I put a parenthesis around this. We are going to learn tonight that this dx is actually multiplied into this expression. So that's going to be in about 20 minutes clear from now. So notation-wise, if I have addition and subtraction inside the integral, I have to put parentheses, because we are going to discover that this dx is actually multiplied into the function f of x. All right, so now you have 2 functions, and you just integrate each one of those independently from each other. That's what the blue rules were for. Knowing that you have a constant of 5 and a constant of 10, which you get to copy. Again, a blue rule says keep the constants outside, don't worry about them, just multiply at the end. So if you don't want to separate these into 2 integrals, you don't have to. You can do it term-wise, right? So without writing 15,000 integrals over here, I'm just going to say that I'm going to rewrite this as 5e to the x minus 10x to the negative 1/2. Because I need to see this exponent so that I can do plus 1 in peace. Now, for the first one, I just copy 5e to the x, because constant 5 you get to just kick out, and integral of e to the x is itself. So nothing new there. Minus, I copy 10, that's the rule. And now I have x to the negative 1/2 plus 1 divided by negative 1/2 plus 1. And then don't forget plus c at the end. Usually I say it's either plus c or minus 1. You make a choice. So now it adds up. I mean, per line, per problem, could be like a minus 20 on a test. So 5e to the x minus 10 x to the 1/2 divided by 1/2 plus c. Now this half from the denominator goes up as a 2, so that makes into a 20. So we have 5e to the x minus 20. There we go. You can put square root of x if you want to be, that's the boss level. And there you go.
Is that boss level better than x to the 1/2?
It's not. It's just boss level. X to the, yes, because you see x to the 1/2, and there is a half a second stutter. If you see a root x, you immediately know. It's a visual thing, right? There is no difference between them other than the visual, right? That's it. And the last example with something a little bit spicier, and then we'll switch to 5.1, is x squared plus x minus 6 divided by x minus 2 dx. Do we have a division rule right now in our life? No. That's in Calc 2. So what is your only hope of solving this problem then? Factor and cancel. If it doesn't cancel, you can't do it right now. You go technology, you use Simulab, you use Wolfram Alpha, right? It's going to plow through everything you put in. But in terms of solving these by hand, if it doesn't factor and cancel right now, you are dead in the water. So this should factor into x minus 2x plus 3, if I did this correctly in my head. And then we see that x minus 2 cancels. So the only thing that I need to integrate is actually, don't forget the parentheses please, x plus 3 dx. What is integral of x? X squared over 2, good. Because exponent is 1, 1 plus 1 is 2, divided by 2. And what's the integral of 3? Integral of 3? 3x. And then we have plus c. So the last thing that I want to work out here, and then we switch to the next lecture, is why and how integral of 6 dx becomes 6x plus c. Would you all agree that there is no harm done if I write it as 6 times 1 dx? Would you still agree no harm done if I write it as 6x to the 0 dx, because x to the 0 is 1? Now, by the rule we covered earlier, kick 6 outside and integrate x to the 0 dx. You know the rule, add 1, right? So 6x 0 plus 1 divided by 0 plus 1, which is 6x to the first power over 1 plus c, which is just 6x plus c. Bueno? Now, clearly, you guys will go directly to this, right? You will not use any of these steps. You will just know that when you are integrating a number, you just pick up a variable. Why? Because the derivative of 6x is 6. Yay, right? Always keep in mind, it's a joke to check these. You take the basic derivative you learned in chapter 3, and if you get this, it's 100% okay. And that's what we have for 4.9, which closes the story on chapter 4 and opens the doors for integration, which is chapter 5, and then the next 4 chapters also in Calc 2. So let's go and do chapter 5 now.